Hello everyone, welcome to this month's speaker series hosted by the Mars Robotics Association. We're based in Mars, PA, and our first robotics team is for grades 4 through 12. This month's speaker is Kathryn Beckwith. Kathryn Beckwith is a native of Mars, Pennsylvania, and graduated from Mars Area High School in 2007. She attended the University of Pittsburgh and earned her Bachelor's of Science in Materials Science and Engineering in 2012. While at Pitt, Kathryn completed 3 co-op rotations with General Electric Aviation in Cincinnati, Ohio. After graduation, she worked for Alcoa Power and Propulsion, now Arconic, in Hampton, Virginia. Kathryn and her husband, Mark, moved from Hampton to Pasadena, California in 2013. Both work for NASA's Jet Propulsion Laboratory in Pasadena. Mark is in mission design and navigation, and Kathryn is a materials and processes engineer. She's an outdoor enthusiast who loves backpacking, hiking, fishing, and rock climbing, visiting Disneyland, and spending time with her husband and their dog, Moose.
Hello, everyone, and welcome to Mars, Katie. How are you doing today?
I'm good. Thank you so much, Owen. I'm very excited to be joining you.
It's good to hear. So, to the viewers at home, you can submit questions using the first link in the description below, and Katie will answer those at the Q&A session at the end of the show. So, you have a presentation for us, so tell us a bit about what you do.
Sure. So I'm a materials and processes engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. I want to just say thank you, first of all, to the Mars Robotics Association for inviting me to give this presentation. I'm so excited to be speaking with all of you. Before we start the presentation, I just wanted to point out the photo in the upper left-hand corner here. This is actually a picture of me next to one of our demonstration models of the Mars rover Curiosity, which is currently on Mars. And what's so unique about this photo is actually the little dots that you see in the wheel, or the holes, mean something very significant to the Jet Propulsion Laboratory. So NASA actually told us, JPL, that we weren't allowed to brand the logo JPL on the side of Curiosity because we are in fact a NASA center. So it's NASA's rover that's going to Mars, which is so true. But JPL has a lot of pride in what we do and the products that we create. And so these holes in the wheels are actually in Morse code, spells out JPL. And so every time the rover wheels would turn on the surface of Mars, you would actually see in Morse code JPL. So we kind of branded the rover, and we branded Mars too, for the Jet Propulsion Laboratory. So that's just a fun little fact that I always like to tell people. And one reason why I'm so excited to be posed next to the rover there. And I think the next slide is, okay, there we go. So I said before that I am a materials and processes engineer. So I think first, before we discuss what materials science is, it's really important to describe what an engineer is. And so an engineer, I found a couple of definitions. Of course, there's many out there in the world, but I found two that I think really describe what an engineer is. So the first is a person who uses science, math, and creativity to solve technical problems. I like this definition because it certainly captures the STEAM mentality, especially creativity. I think in order to be an engineer, you need to have some artistic quality. And the second, I found this definition, and the reason why I like it so much is because it specifically mentions the word materials in it. So an engineer is the profession in which a knowledge of the mathematical and natural sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. So I hope this presentation really helps you to understand what materials science is. But as I said in the beginning, I'm also a processes engineer. So I wanted to find a definition that captures process in it as well. And I found the definition for the verb engineer, which is to engineer is to create, plan, build, or design a solution or process. And can we go to the next slide, please? Okay. Okay. So material science, in my opinion, is at the intersection of chemistry and engineering. I feel that it's all about taking and understanding materials and the chemical and physical processes in order to create new ones. But what are materials? People always ask that. What are materials? Well, materials, in one word, it's stuff. It's everything and everywhere around you. So materials are from plastic Legos that you see pictured here, to the carbon fiber phone case, to ceramic mugs, to jet engines, which this holds a particular special spot in my heart because I got to start in working on the high pressure turbine section of both commercial and military jet engines, which I'll talk about a little bit later. Two, I couldn't not mention the steel bridges that are everywhere in Pittsburgh. So materials are everywhere around you.
So what would be the difference between a mechanical engineer and a materials engineer?
Well, that's a great question, Owen, and I get that question a lot. So mechanical engineers are really responsible for designing things, but material scientists engineer the stuff that makes up those things. And many wonder, what is material science at NASA? Well, in a phrase, it's extreme engineering. We're dealing with the harshest of environments, from Earth orbiters to the radiation-laden moon of Europa, which is a moon of Jupiter. And you can see that in the bottom left-hand corner of the screen, to interstellar space. So if you followed our missions, especially the Voyager missions, both of those spacecrafts, Voyager 1 and 2, have reached interstellar space. So that's an example of an extreme environment that we operate in. But probably our most popular environment is Mars, the planet Mars. Not Mars, PA, the town, but Mars, the planet. So a couple of fun facts about Mars. Its atmosphere is about 1/100th of what it is here on Earth. So it's a very thin atmosphere. And it's also pretty cold there. It gets to a minus 285 degrees Fahrenheit, and it gets as hot as 85 degrees Fahrenheit. So you might remember last year, we actually launched our next rover, and it's headed to Mars right now, scheduled to land on the surface on February 18th of this year. So we're a little less than a month out. And what's so great, in my opinion, about the rover is that it actually has a very interesting hitchhiker tagging along. And so the next slide, we're actually going to show a video of the first helicopter to fly on Mars, Ingenuity. So let's learn a little bit about Ingenuity.
Sometimes you have to do something just to show that you can do it. When the Wright brothers flew for the first time, they flew an experimental aircraft. And in the same way, the Mars helicopter is designed to show that we can fly powered helicopter flight in the Martian atmosphere.
From day one, this was the unwavering dream of our team, to get our helicopter launched to Mars so that we can get that opportunity to do that very first rotorcraft flight test in the actual environment of Mars. It's extremely difficult to fly at Mars because the atmosphere is so thin. Compared to Earth, at Mars it's less than 1%. So the first and foremost challenge is to make a vehicle that's light enough to be lifted. And then the second is to generate lift. The rotor system has just been very fast. 2,000, 2,200, 2,400, 2,600. We're spinning between 2,000 and 3,000 revolutions per minute, and it takes a lot of energy. So it's that balance of a very light system, yet having enough energy that's needed to spin the rotor so fast to lift, and on top of it, having to design in the autonomy.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
Our experiment window is 30 Martian days. So we have planned up to 5 flights of incremental difficulty.
The very first flight, the main thing is we want to get the legs off the ground, and so we will basically go up about 3 meters, and we'll hover there and then we'll come down again. And that will be the first, really major milestone.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out, 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
At this point, we've tested all we can on Earth. We have mathematical models that shows how it'll fly at Mars, and we've tested it in the simulated environment that we can create on Earth. It really is time now to do the real flight tests at Mars.
Nothing is a given, but we have done everything we can in terms of a test program here on Earth. The vehicle's performing extremely well so far. It's been doing exactly the right thing, even right now when it's bolted onto the Perseverance rover. So there's a very good chance that we'll pull it off, yes. But it's still high risk, and none of us forget that you could have a glitch that, could mean end of mission, yes.
It's going to be exciting, reacting to any surprises we have. We can't wait. What's really most important is everything we're learning here is for the future rotorcraft systems that we want to introduce into space exploration.
So that's a great video. I've spent the majority of my career at JPL working on Ingenuity. So it's really touching. Every time I watch that video, I'm reminded of how special and unique it is to be able to work on this project, but also to have the opportunity to put a craft like this on Mars. This is a Wright brothers moment for sure. So as we heard in the video, the vehicle needs to be incredibly light in order to generate enough lift. Remember, the atmosphere on Mars is very, very thin. As a materials engineer, what's so great is the vehicle actually can utilize materials to lessen its mass.
Yeah, so how light actually is it? Because it looks, pretty large in the...
That's a great question. So I think many are going to be surprised that first, something Owen and I were talking about earlier is the size of the vehicle itself. And I think many are going to be surprised that from tip to tip, it's about 1 meter. So about 3 feet from tip to tip, the blades. And the whole vehicle weighs only about 4 pounds. So we put a lot into a very little package, and you can see the challenge of needing to create enough lift in order to fly on Mars. So as I was saying before, the materials are really a critical component to meeting the mass requirement. And one class of materials called composites are utilized heavily throughout the design of the helicopter, and specifically carbon fiber composites. You can see them used in the blades and also the legs. So I want to ask a question, and you can kind of mull this over at home, and we'll go through the answer here in the next slide. But I want you to think, what do a pencil and carbon fiber actually have in common? And so in the next slide here, I'm giving a little hint before the actual answer. So if you remember back to your general chemistry classes, the number of protons in the nucleus of an atom actually equals the atomic number of the element itself. So in this picture here, we're showing 6 protons in the nucleus of this atom. And if you recall, that's the element carbon. So carbon is the commonality between your traditional lead pencil, and carbon fiber. So remember before I said that materials science and engineering is at the intersection of chemistry and engineering. So let's be chemists for a minute, and let's pretend too that we have a very high magnification microscope. And here we can see many planes of carbon atoms arrange themselves in almost sheets. Now, in the sheets or in the planes of the carbon atoms, the carbon itself is bonded to other carbon atoms via covalent bonds. And you might recall the covalent bonds are actually the sharing of electrons between two atoms. This is a very strong bond. So within the plane of the carbon atoms, we have a lot of strength. But between the planes, it's actually very weak. And this is how you write with your lead pencil, which isn't lead, it's actually graphite. When you're writing, you're depositing layers and layers of carbon atoms, graphite or graphene, onto pieces of paper, and you're shearing off those layers of atoms. Now let's imagine that we take all of those carbon atoms and we actually turn them vertically. Now you can see that the atoms are running in a north-south direction. So if I were to pull in a north and south direction, it would be very difficult for me to pull the carbon atoms away from each other, again, due to those covalent bonds. So this is the direction of strength. Now, again, if we pull east and west, it's going to be very easy to pull those layers apart from each other. In material science, when a material has different properties in different directions, we call this anisotropy. Now, I'm going to do a very quick, simple little demonstration here with 2 sheets of paper. I want you to just pretend that these sheets of paper are actually sheets of carbon atoms here. So again, if I stack the carbon sheets one on top of each other, it's very easy to pull the sheets away from each other. But in the north and south direction, it's very difficult for me to pull the pieces of paper apart from each other. I really can't do it. Even the single sheet, if I just use a single sheet of paper, it's very difficult for me to rip this piece of paper in the north-south direction. So just imagine that we take multiple sheets of paper. So here I've got 2 plus many more, and I just start folding them in kind of a random pattern so that they're mechanically affixed to each other. And here's a view of the top. So what you see is actually what's shown in the sketch here on the left-hand side, a bunch of sheets of carbon atoms now folded together. And again, if I'm pulling in the north and south direction, it's very difficult for me to actually pull the sheets apart from each other. So we have a lot of strength running along the fiber or the long axis of this material. Okay, and so in this image here that's shown, we can still see the sheets like this kind of pattern in the right-handmost portion of the image. And this is just all of those folded carbon atoms that are mechanically affixed to each other. When we take our pretend microscope and we actually decrease the magnification, now we can see what looks like a fiber in the very leftmost portion of the image. So all of these carbon atoms that are folded together actually come together to create what is a fiber. And along the axis of the fiber is where we get all of the strength. So I'm showing the direction of strength here. So these images are taken with what's called a scanning electron microscope. And the magnification actually varies from 8,000 times, which is at what magnification this fiber was taken at, to 50,000 times magnification. So that may or may not mean something to you. So I want to show you relative what the fiber size is relative to something very common. So we see here the carbon fiber, and it's on the order of, if we look at the scale bar down here, it's on the order of about 6 microns. Well, how big is that? Here's a picture of a human hair. So we're looking at a material that's very small, and it's very thin, but it's also very strong. So in this graph, I'm showing the specific strength of the material of actually 3 different common aerospace materials: 6061 T6 aluminum, titanium, and carbon fiber. So you can see immediately that carbon fiber has a much higher specific strength than aluminum and titanium. But why is that? Well, remember, we're not just scientists, we're engineers. So we really need to understand the mathematical component of what specific strength actually is. So specific strength is defined as the strength divided by density, or sigma divided by rho. So in order for the specific strength to be very high, we either need to have a very high strength or a very low density material. In the case of carbon fiber, we have both. The density of carbon fiber is about 2 times less than that of aluminum. And so that'll compensate for quite a bit of the specific strength that you see of carbon fiber, but it doesn't count for why the specific strength of carbon fiber is so much greater than that of aluminum or titanium. That's because the strength, the actual inherent strength of the material is so high. So again, those covalent bonds are really helping us maintain strength in the material. So in this next video, we're going to show more examples of why carbon fiber is so strong, and you're going to be able to see carbon fiber at the optical scale, but you're going to be able to see it in tiny little slides. So it'll give you some perspective on how tiny the carbon atoms are, but how they make such significant impact on the macrostructure of materials.
Hey everybody, today I'm going to be showing you the strongest material known to man, graphene. It's 200 times stronger than steel. Now what's amazing about this piece of graphene I have here is that it's only 1 atom thick. So this sheet that I'm holding is obviously not the graphene. This is not 1 atom thick. And on top of it, there's a quartz plate. That's not the graphene either. But on the quartz plate, there's a 1 atom thick piece of graphene. So how thick is 1 atom thick? Well, this paper that it's on is around 650,000 atoms thick. So you can see how thin it is, and this is 650,000 atoms about. So this means that because graphene absorbs so much light, you only need a few sheets of it, only a few nanometers, in order to block all light. For example, here's some stacked up layers of graphene, also known as graphite. And you can see how it's completely opaque, metallic looking. But what if we wanted to actually start with graphite and get graphene out of it? Is it possible? Well, a few years ago, it was thought that it was impossible to get graphene from graphite. But it turns out all you need is a little bit of Scotch tape. So I'm going to be using this type of pencil that has a lot of graphite, but you can actually use one that doesn't have a lot of graphite in it as well, and you should still be able to find pieces of graphene. So pretend that this is a layer of graphite. What it really is a stack of hole punched pieces of paper, but they're all stacked together. So this is equivalent to a little piece of graphite that has layers of graphene stacked. So we're going to get our tape and put our graphite on it, and then we're just gonna fold it together, and every time we touch it together in a spot, it's gonna pull off some layers. And we're just going to keep doing it, and each time we do it, it's going to pull more and more layers off of the graphite. See, and if you do it enough times, you'll end up with single layers of graphene in some spots. Okay, so I'm just going to make a tiny dot with the graphite here, and then get some Scotch tape. And then you just transfer it onto the tape, and then from here, you just keep folding the tape, sticking it together. So you just stick it together, and then pull it apart. And stick it together and pull it apart. Okay, so what you're going to end up with is just kind of a bunch of smudges on the tape here. Now if you can keep track of the dot and look at the dot that has been transferred the most number of times, that's the spot where you're most likely to find graphene. Now even though graphene is so strong, before 2004 it was thought that a single monolayer of graphene was impossible to make. They thought it was thermally unstable and it couldn't exist. Now because this upended the traditional thought that you can't make pure graphene, and also because they did it with such a simple method, that actually won them the Nobel Prize in 2004. Now if you don't have these sheets of graphite, you can actually just use a pencil. So pencil lead is actually made of mostly graphite. The softer the pencil lead, the more graphite there is in it. Okay, so now all I've done is stuck the tape on a glass slide here. I sprayed some glue on the glass slide and then stuck the tape so the sticky side is up. And we're going to look at all the spots that I stuck a lot of times with the graphite pencil there. So we're going to be looking for any layers that we can see that are actually allowing any light to pass through. So these particles are really small. That's because we're using graphite from a pencil, and so it was already ground up to very small pieces. Now you have to be careful when you do this because you might be mistaken for some layers that look like they're graphene, but they're actually most likely just your skin cells because you're using your fingers to pull the tape apart, and it's really easy to get your skin cells stuck to it. The way you can know that they're most likely graphene is they're going to be the same size of chunks as the dark spots. They're not going to be bigger than that. Okay, look at that. We've found some graphene. So notice how all the chunks around it are dark. That's because there's multi-layers of graphene in those, so it's still considered graphite because each individual atom thick layer of graphene absorbs around 3% of light. So you can see you only need a few layers of it before you actually have a dark material because it just absorbs all the light that goes through it. Probably letting around 80% of light through it there. You can tell that's only a few layers of graphene there. And thanks for watching, and I'll see you next time.
Okay, well, I know what I'm going to be doing once I'm able to get back on lab. I think I'm going to get some of my lead pencils out and some Scotch tape and actually run that experiment. I've never done that before, so that inspired me. I just found that video kind of serendipitously recently, and I thought that it was very relevant to this talk, but also very interesting. So you can see, through the description of carbon fiber, its specific strength, why we would choose to use that material in the design of various Mars helicopter components. So outside of Mars helicopter, what is a typical day at NASA's Jet Propulsion Laboratory? Well, I put a list here of various things that I do. I certainly don't do all of this in one day, but these are all of the tasks that my job consists of. So developing and implementing mechanical test plans. When I said before about actually pulling those sheets of paper in kind of a north-south direction, that's actually called tensile testing, and it's something that we do commonly on lab. And of course, with testing, there's always data that comes with it. So I compile and analyze test data. I also assist designers or mechanical engineers in material selection. And then I also review the materials that comprise their designs for approval. I said before about how we operate in very harsh conditions. Well, when we're operating in harsh conditions, we often have a lot of requirements on what our designs must look like and what our materials must be like. And so I'm following those requirements and making sure that designs actually meet those requirements. I perform failure analysis using tools like the scanning electron microscope that we discussed earlier in the image of the carbon fiber and the carbon folds. I also manage teams, attend meetings and support reviews. I write technical reports and documents, and I also give presentations. And all throughout the day, you'll find me drinking plenty of coffee. So how did I get here? Well, Owen gave me a great introduction, and I'm just going to repeat some of it, hopefully with some new information too. So I am a graduate of Mars Area High School. I graduated in 2007. In high school, I took as many science classes as I could. So I think I took 7 in the 4 years that I was in high school. I hope that they let students take more now, because that was always my goal, was to take more science classes in high school. I couldn't get enough science, and so I attended governor's school for healthcare, and that was a mini medical school experience. And then on the weekends, I also went to the Westinghouse Science Honors Institute. And I even participated in a Women in STEM Day at Carnegie Mellon University. And I have to credit CMU with exposing me to material science. It was at CMU that I first heard about material science and engineering, and I really fell in love with it. After graduating from high school, I attended the University of Pittsburgh, where I earned my Bachelor of Science degree in Material Science and Engineering. And while I was at Pitt, I completed 3 co-op rotations at General Electric Aviation in Cincinnati, Ohio. This is where I worked on commercial and military turbine engines, and I was exposed to the high pressure turbine section of those engines, where we worked on nickel-based superalloys. I worked on failure analysis, and I did some research while I was there too. It was a natural progression then, after I graduated from college, to go and work at Alcoa Power and Propulsion, now Arconic. And there I worked on industrial gas turbine engines. I was there for about a year before my husband and I moved to Pasadena, and both of us started working at JPL. And I'm going to be celebrating my 7-year anniversary at JPL this coming March. So it feels like I've been there for only about a year, but the time just flies by. So I can't believe that it's been 7 years already. And so one of the best things about working at JPL is actually being able to live in Southern California. So Los Angeles, which JPL is just right outside of Los Angeles, about 20 or 30 minute drive outside the city, there's plenty of entertainment here. We get to see the Pittsburgh Penguins come into town, and we love to root for them when they're playing against the LA Kings. And we also get to see a lot of great concerts. In the not last year, but the year before that, we got to see Elton John and Paul McCartney play at Dodger Stadium, which was amazing. And we also love to go to Disneyland. Disneyland is in Orange County, which is only about an hour drive from Pasadena. So we go there as often as we possibly can. But I have to say, my favorite part about living in California is all of the outdoor activities that it offers. I love backpacking and hiking and fishing and rock climbing. And so some of my favorite places to go to are in Central and Northern California, Lake Yosemite Valley, the Mammoth Lakes area, Mammoth Mountain. And then I also included a picture of my first fish that I ever caught fly fishing in the Merced River, just outside of the Yosemite Valley. This was just taken about 3 years ago. And my husband and I actually just moved. We moved to a little town called Sierra Madre. It's still proximal to the city, but I have to say it's probably the most East Coast town on the West Coast that we could possibly find. So it feels like home, but a home away from home. So again, I just want to thank everyone for listening. I know that we're going to have a Q&A portion here, but I just want to reiterate my thank you to the Mars Robotics Association and to all of you for listening.
Yeah, so awesome. We're going to move into Q&A now. So as I said at the beginning, there's a link in the description where you can go submit your questions, and if we have time for all of them, if we get through them, then Katie will be able to answer that question live. So the first question we have is, what is your favorite part of your job?
So my favorite part about my job is that I'm constantly learning. No day at JPL is the same as the day before it. And the more that I work on flight projects and the more that I work at JPL and the more people that I work with, it seems like the less that I know. And I like that. I really love learning. It's a very academic setting. And we are managed by the California Institute of Technology. So it feels like a college campus on lab. And certainly people think in a very academic way. And so I just love the challenge and the diversity of learning that the JPL offers.
Yeah. Next question is, so this is worded a little bit in a complicated way, but so one can test the lower atmosphere of Mars on Earth, but how do you take into account the lower gravity of Mars with building the helicopter?
That's an excellent question. So we can't test lower gravity on Earth. I think that we've all seen the astronauts that go up in aircraft, and that's how they kind of simulate the weightlessness by that hyperbolic arc. But we certainly don't do that with our helicopter. So one of the ways that we account for the difference in gravity is actually by the mass of the vehicle itself. So that's why we have to make the vehicle a specific mass in order to account for not just the gravitational differences, but also the atmospheric differences between Mars and Earth.
Yeah. So how long did it take from the initial idea of coming up with Ingenuity to actually getting it launched and sent to Mars?
That is a great question. I think that the answer is going to surprise you. So Ingenuity, the idea was born many, many years ago in the early 2000s, late 90s time period. The chief engineer who you saw in the video, Bob Belaram, he actually started thinking, well, I wonder if we could fly a helicopter on Mars. And so he always had this concept kind of in his head. And it was actually around the time when I joined JPL, about 2015, when we started doing demonstrations with smaller vehicles. And then we started building larger vehicles, ones that are representative of the vehicle that you see today. And so we really went from 2015 to 2019, 2020, building a vehicle, which is rapid on the time scale of building spacecraft. If you think about Mars 2020, it's been in work for many, many years. And it's not just been in work, that particular rover, but it's an evolution of rovers that came before it. But the helicopter is a novel spacecraft. It's a novel aircraft. So to go from a technology demonstration to a vehicle that's going to, we hope, fly on Mars is a really rapid progression.
Yeah, that definitely is. That's a much shorter period of time than I thought it would be.
Yeah.
Yeah. So next question is, what should someone major in if they want to kind of do what you do, working for NASA, working for JPL?
So I think the great thing about working for NASA, not just JPL, right? Working for NASA in general is NASA requires all kinds and all types to make its programs and its missions successful. You don't necessarily have to be an engineering student to work at NASA. You can, and certainly I encourage those of you who want to be engineers to pursue engineering, but you don't have to. We have plenty of scientists, we have geologists, we have biologists, astrobiologists, cosmologists, etc., that work at NASA, and not even in just science and engineering, but we have I think some of the best artists in the world. And heck, that video that you saw was a production done at JPL. So we also have really great producers creating that media that we can all get to enjoy. So yes, you can become an engineer and you can work on more technical projects, but your options are not limitless. Certainly, you can work in really any discipline that you want to at NASA.
Yeah. So next question is, with graphene being such a new material, what was used for the older rovers and what was kind of used before that kind of was existed?
That's a really great question. So I will just say again that the helicopter is a novel craft. It is a first of its kind. There hasn't been one before it, but carbon fiber has been used fairly recently, but on the rovers, we typically use a lot of metallics, and that's because of the structural support that we need, the mechanical support that we need from the vehicle itself. There are advantages to using particular materials and materials classes over other ones. And that's what's so exciting about being an engineer, being a materials engineer, is you really have to think critically about what fits this particular need. So there could be different materials that kind of fit the equation, but you have to pick which ones fit the design requirements, the environmental requirements, the mission requirements. And so not one material fits all designs or fits all of those categories.
Yeah. So now a more hypothetical question is, do you have an interest in traveling to the planet Mars someday, if that happens?
You know, I think that someone needs to go to Mars eventually. Would I like to go? I don't know. I've thought about it. I don't know that I've come to a conclusion yet on that. I think that certainly the technology is evolving to a point that we can sustain humans on Mars successfully. And so I think that there's a lot of potential there. But I do have to say, I really enjoy the Earth so much. I think that Earth is such a unique and special place. And I love exploring it. I love being on it. I love being a part of it. And so I would certainly miss Earth if I were to go to Mars.
Yeah. Yeah, I think that would be the biggest difficulty, is not being able to like go on a hike outside or like go ride your bike.
But you know, Owen, it's really interesting because Mars and in that image that I showed of Mars and one of the slides, there's this very large valley that actually runs across the surface of Mars, and it's called Valles Marineris. And Valles Marineris is incredibly huge. It's actually it's as long as the United States, the continental United States, and it's incredibly deep. So I often think, how cool would it be to go for a hike in Valles Marineris, or to explore, you know, some of the geological structures of Mars. So I certainly think it would be a great opportunity for exploration.
Yeah. So next question is, how do you make the testing equipment light enough to fit in Ingenuity?
Oh, okay. That's a great question. So there are many ways that we do that, and I think, you know, this is actually kind of related to the question that Owen was asking before we started the presentation, which is, you know, how do you kind of fit that mass margin? That's such a low mass vehicle. It again, it weighs 4 pounds, right? So you have to be thinking critically about every single gram and tenth of a gram that you put on the vehicle. Now, in terms of the test equipment that we use to actually test the vehicle, what's so awesome is that JPL has fantastic environmental test resources where we can simulate the atmosphere of Mars at the density of Mars, and we can actually fly in a Martian-like environment here on Earth. So we are lucky that there are many missions before us that have funded these kind of institutional assets like our test equipment that have allowed us to fly and utilize in the development of and testing of the Mars helicopter.
Yeah, so next question is, how did your past job experience help you when you came to JPL and NASA?
Oh, that's such an interesting question. So So one might think, oh, aerospace engineering, it's all kind of the same, you know, working on jet engines and then coming to the Jet Propulsion Laboratory. I mean, it has jet in its name, right? It must be similar, but it really was a left-hand turn for me. So I think what's so interesting is I started working very heavily in metallics, nickel-based superalloys. And if you think about launching a vehicle off of Earth's surface, it's all about launching a vehicle that is low mass. And nickel-based superalloys are not low mass materials. And so I really, I took what I took from my previous job was actually the critical thinking skills, the engineering kind of mindset and the critical thinking skills, not so much what materials I worked on, but how to think about designing materials, implementing materials, processing materials. And then of course, I really relied on my education. I had to go back and kind of re-educate myself on some of the different material classes that I had learned about while I was at the University of Pittsburgh.
Yeah. So going back kind of even before that, how did you know that you kind of wanted to be an engineer and pursue that path? You had said that you took a lot of like science classes in high school, but
yeah, so so I know that my parents are listening right now, so I have to tell this story, and I tell it all the time. I first really got hooked on science when my dad took me on a drive on Route 228 to look at the comet Hale-Bopp. I think it was back in 94, 95, 96 time frame. And I remember just being in awe that this thing was out there flying past us. And I just kind of got this sense of how unique and special we are. And I just wanted to learn more. And so I started learning more about space because I thought, well, you know, if this comet Hale-Bopp has anything to do with space, I'm probably going to like space. So I started learning about galaxies and planets and other star systems and nebulas and white dwarfs and all of these different celestial bodies. And that then in turn led to, well, okay, I'll take biology. And then my biology teacher said, well, why don't you take anatomy and physiology? And I said, well, okay, you know, I'll take that too. And then, you know, I just started poking at different aspects of science. And eventually, you know, I landed on engineering because I really, specifically material science and engineering, because I loved the marriage between science and mathematics. I was pretty good at math, but I always really wanted to keep science kind of in the forefront of whatever I did. And so I determined that material science would be just an excellent fit for me. And I knew that I loved space. So working at General Electric Aviation kind of came naturally. And then of course, landing at JPL was just a dream come true.
yeah, kind of the next question actually goes further along that line is what would be your dream accomplishment at JPL or NASA?
Oh my gosh. You know, my gut reaction and my first thought is that just getting to where I am today is such an accomplishment. Everything else that I do after that is just extra. It's just extra. But I think having this helicopter fly on Mars is going to be one of the biggest accomplishments of my life, because I personally put a lot of energy, time, and love into that vehicle, into the project. And I've never wanted something to succeed as much as I want that helicopter to succeed. So I think that in the coming months, it's going to be really exciting to see that vehicle perform. Outside of the helicopter, I I can only imagine JPL has some really amazing missions coming up, like Europa Clipper going to Europa, that moon of Jupiter that is just bombarded by radiation constantly. I could only imagine potentially finding biological signatures on a moon like that, and being able to say that we're not the only ones here in this universe would also be very cool. So perhaps, finding life on another body would be an accomplishment that I would like to be a part of.
Yeah, that would be really cool.
Yeah.
So we're almost done here. So the last question is a question that we ask at the end of every show, and it's, what is the best advice that you've ever received?
Okay, so I knew this question was coming up, and I'm going to be forward with the audience and saying I knew this question was coming. And I actually took a lot of time to think about this. And I wrote down several things, and I really thought about it over several days. And I have to be honest, I think the best piece of advice I've ever been given is something that actually my husband was given, but he relayed to me. And that was a professor. So he went to the University of Notre Dame for his undergraduate degree. And his story was, he had this professor who told my husband, Mark, you're in the driver's seat, so drive. And I feel like that's so true. You are in control of your life. If you want to work at the Jet Propulsion Laboratory, you can work at the Jet Propulsion Laboratory. If you want to work at General Electric, you can work at General Electric. Whatever you want to do, you can do. And I've tried to really remember that when things seem to be getting difficult, that I'm driving, that I can manage this, I can handle this, that if I want to work on a mission like Europa Clipper, I can go ask to work on a mission like Europa Clipper. If I want to go work in geology, I can say, hey, I want to go work in geology, and I want to learn about that at JPL. So I think it's really just saying you have control of your life, and if you want it, go get it. The world is your oyster.
Yeah, awesome. So that's great advice. Thank you for coming and presenting and sharing your knowledge with us. So, and thank you to everyone watching.
Thank you. It's been a real pleasure. Thank you, Owen.
Yeah, thank you. So join us next month for a special live episode featuring coverage of the Mars Perseverance landing, and that'll be at approximately 3:55 p.m. on February 18th. And a NASA expert will be there to answer questions, which viewers can submit before next month's episode using the second link in the description, which is titled February Questions. So the Mars Robotics Speaker Series is a production of the students of the Mars Robotics Association. Mars Robotics is part of First Robotics, with teams competing in First LEGO League and First Technical Challenge. For more information on the Mars Robotics Association, the Mars Robotics Speaker Series, or any of our other programs, please visit us online at www.marsroboticsassociation.org. Thank you for watching.